So the Coriolis effect is a result of the Earth's rotation, causing moving objects to follow curved paths. In the northern hemisphere, the curvature will be to the right, and in the southern hemisphere, the curvature is to the left. Now, there are some changes with latitude. So if I were to draw the Earth, a really poor Earth, and we have the equator right here, and you have to excuse me, I've forgotten my ruler. 2 seconds. There we go, my apologies. So at the equator, which is right here, there's going to be no Coriolis effect. But as you go up, the curvature will become more pronounced. As you go down, the curvature becomes more pronounced. So as you, the North Pole and South Poles will have the maximum amount of Coriolis effect, whereas the equator will have no Coriolis effect. So as the Earth rotates, different latitudes are going to be traveling at different speeds. And the change in speed with latitude causes the Coriolis effect. Now, this is a very abstract idea. It's very difficult to imagine that different parts of the same ball are traveling at different speeds. So, to kind of show you how this works, take a look at this diagram right here. So, here we have, if we were to take the globe and spread it out on a flat surface, here, and please excuse me on my drawing, I don't have my normal equipment with me. Here you see that the straight line is curved because the Earth is curved. So here you have another straight line. Okay, so this straight line will pass at the same amount of time, but a different distance. So right here, okay, is roughly 500 miles. Okay, and 1 hour to make this line go line. I'm gonna label this to make this easier for you guys. This is going to be line 1, and this will be line 2. So for line 1, in 1 hour, if we are at 60 degrees north latitude, it would take, in that 1 hour, it would travel 500 miles or 800 kilometers. In 1 hour, from line 1 to line 2, at 30 degrees north latitude, it's going to travel 1,400 kilometers or 870 miles in 1 hour. This is all because of the curvature of the Earth. And down here at the equator, from line 1 to line 2, to go in 1 hour, it'll travel 1,000 miles or 1,600 kilometers. And so in different places on the Earth, it is traveling different speeds, because what is speed? It is distance divided by time. And if it takes this one longitudinal line 1 hour to move that distance, we can easily figure out its speed. And because of the curvature of the Earth, different parts are going to rotate at different rates. So the change in speed with latitude causes this Coriolis effect. So if the Coriolis effect didn't exist, what we would expect would be global wind patterns only influenced. So if our entire globe went at the same rate, we would expect global wind patterns that would solely be influenced by the heat of the sun. And so we would only have 2 convection cells. But as we saw yesterday in our lesson, or excuse me, last time in our lesson, that's not the case. We have several convection cells. And so we would only, basically, we'd only be seeing this big convection cell if this didn't happen. So this also, if you want to just kind of take this in a different direction, this would be what we would see if our planet were, tidally locked or didn't rotate at all. But the Coriolis effect is going to break up our global circulation. And on Earth, the large circulation cells break up into 3 smaller ones, moving diagonally. So other planets are going to have more or fewer circulation cells depending on their rate of rotation. And please remember always, this is not the scale. And so we can see all these different circulation cells. We have 1, 2, 3, 4, 5, 6. And this is all caused by that Coriolis effect. Like we saw in the last one, if we didn't rotate, or if our rotation was smaller, we might only have 1 circulation cell. But because of this different rate of rotation, because of the way that we are spinning, we have 6 total circulation cells instead of 2. So how does the ocean factor in to circulation? Well, it actually has a role in this. Now, if you remember on the last lesson, we discussed land breezes and sea breezes, and how the ocean absorbs and releases heat at a much slower pace than the air over land does. So the ocean slowly absorbs and slowly releases heat energy, helping to keep Earth's temperatures relatively stable. It gets colder faster on land than it does on the ocean. And the oceans heat or cool the air above them and transport heat around the globe in currents themselves. Now, when it comes to weather for this, hurricanes form over warm ocean water, drawing their energy from the water's heat. And so literally hurricanes are powered by warm water. So ocean currents, much like the air currents that we've talked about in the jet stream and the big large convection currents, are large scale water movements. They occur everywhere in the ocean, and they're both on the surface and deep within the water. And so these are going to be moving warm or cold water. It's a convection current essentially, that runs through our oceans. When just thinking of a movie example, Finding Nemo. They find the Australian current and use it to move quickly. And so that current is part of this large scale movement of water. So there are two main types, and you make sure to write this correctly. You have surface currents, which make up about 10% of all ocean currents, so a small amount. These surface currents are primarily driven by wind, so the effects of those winds hitting the top of the surface and moving water. And then you have subsurface currents, which are about 90%, and these are deep currents are driven by density. Now, if you don't remember from our last lesson, we talked about high pressure and low pressure. And let me actually change that color. Which high pressure means dense or cold, and low pressure is less dense and warm. And so on the last lesson, what I did is I drew some boxes to kind of give you guys an idea about this. And so I'll do that again, just in case you weren't here. Okay. And so the cold or high pressure water will be basically filled up. Whereas the warm water will be less filled up because the materials are spread apart. And so this creates our convection currents in the ocean, creating these density-driven subsurface currents. So these cold water currents will fall, and these warm water currents will rise, just like air. So other forces affecting the currents would be things like the Coriolis effect, friction, gravity, thermal expansion, the geologic shape of an ocean basin. And by geologic shape, like how deep it is, and stuff like that. So let's talk about current gyres. So gyres are large circular moving loops of water. And there are 5 main gyres, one in each ocean basin. You have the North Pacific, the South Pacific, North Atlantic, South Atlantic, and Indian. So the North Pacific gyre is right here. The South Pacific right there. The North Atlantic right there. South Atlantic, and the Indian. And so generally, these are going to have 4 currents in each gyre, and they are going to be centered about 30 degrees north or south latitude. So you can see how they start to turn, almost all of them, right around that 30-degree mark, and I did that one a little high. But you can see we also have warm water currents and cold water currents going through them. Now these large currents, while you guys are writing this down, are actually really important. They allow our planet to keep very stable with its temperature. And that's why some of the issues brought up with global warming is such a big deal. Because if we were to lose our ice caps completely, a large influx of colder water would be put into our oceans, which would cause our circulation in our oceans to get thrown out of balance. Therefore, it could actually cause our currents to stop and cause issues with not only our stabilization of our temperatures, but could also impact ocean life, causing a mass die-off of oceanic creatures. And so we can see these right here once again. And of course, there are smaller ones speckled throughout and all that kind of stuff, like the Gulf Stream and the Alaskan Current and the Labrador, the Antarctic one and the Brazil and all that kind of stuff. But for the most part, they are part of these larger currents. These 5 are our major ones. And I believe this is the one featured in Finding Nemo, the East Australian Current. And when I'm talking about that these have effects on the temperatures, let's take a look at something. So this right here, and see if I can make a straight line, and I apologize if I can't. So here is London, Britain and France. So what you'll notice, if you're just focusing here on the United States, you'll notice that these actually line up with places like Canada and Minnesota. France has the same latitude as parts of Minnesota. But why is Minnesota much more cold than France? And it's because it actually has this warm water current. Both these two countries have this warm water current running right by it. And that has a huge impact because remember, it's going to be releasing heat energy very slowly. And so that's going to help keep those areas very much more warm than what they'll be over here in North America. So those were our subsurface, but here we have our wind-driven surface currents. And this is, if you remember yesterday, or last lesson, excuse me, when we looked at the trade winds, you'll notice a very, very similar pattern here in North America and Europe and Africa. And so these currents are driven by the wind. So let's take a look at something really quick. This was an incident that actually happened. So 29,000 rubber duckies, 29,000 rubber duckies, fell off a boat that left China in 1992, and they started to drift across the ocean. January 1992, it was shipwrecked in the Pacific Ocean off the coast of China. By November 1992, half had drifted north to the Bering Sea and Alaska. The other half went south to Indonesia and Australia. From 1995 to 2000, they spent 5 years in the Arctic ice floes, slowly working their way through the glaciers. By 2001, the Duckies bobbed over the place where the Titanic had sunk in the Atlantic Ocean. But in 2003, they were predicted to begin washing up on shore in New England, but only one was spotted in Maine. In 2007, a couple duckies and frogs were found on the beaches of Scotland and southwest England. So these currents are able to take lots of material all around the world. And that's why they're so good for shipping and things like that. But also, anything that we put into our oceans can be carried around the world and have an effect on the entire ecosystem. So some other effects of wind on water movement. You have downwelling, which is a result when two wind-driven surface currents collide, or when a wind-driven surface current collides with a landmass. And so this can cause them to, when the wind-driven is being pushed together, pushing some of that current under. Then we have upwelling, which is the result when two wind-driven surface currents move away from each other, or when a wind-driven surface current moves away from a landmass. So, surface and deep sea current interactions. Kind of the idea is it's this giant oceanic conveyor belt, where because of convection currents, we have shallow ocean currents and deep ocean currents that move all around the globe. And so that higher density cold water is going to be forming our deep ocean currents, while that warmer, shallow water will be forming our warmer, less dense water will be forming our shallow ocean currents.